Exponents and logs lesson number 2. This is a fun part. We actually get to solve equations. So in order to solve equations, you are going to have to remember laws of exponents. So let's go through these pretty quickly. Remember, the idea here is that you can pause, rewind if you need to, so please do that if necessary. When you're multiplying with the same base, add your exponents. The base does not change, you're just adding your exponents. Dividing with the same base, subtract your exponents. Now this is a really, really, really important one. We're going to see this a lot. When you have an exponent raised to another power, that answer ends up being the product of the two exponents. Base, again, stays the same. Exponent becomes the product of the two exponents. Now the next two are, if you have factors in a bracket, the exponent applies to both factors. The exponent is distributed to both. If you're dividing, if you have a fraction in a bracket, for example, the exponent applies to both numerator and denominator. If you have a negative exponent, so this integral law or rule is, if you have a negative exponent, we talked about this in lesson 1, a negative exponent means it's 1 over the positive exponent. So when we have, okay, 1 second here. All right, let's continue now. The rational exponents is when you have a fractional exponent, and if you have a fractional exponent, really important to remember the denominator is the root and the numerator is the exponent. Denominator is the root, so if it was 1/2, it would be a square root. If it was 1/3, it would be a cube root. If you have an exponent that is 2/3, then it's a cube root squared. The numerator is the outside exponent. All right, now zero property is one that we mentioned, we looked at yesterday, is any term raised to the exponent of 0 equals 1. It does not matter what the base is. Okay, I'm going through this pretty quickly. Let's get to equations. Now, if we want to look at these equations, and these are not exponential equations, but they are important examples to look at. We'll be using these type of questions later in the unit, so we need to be able to get rid of an exponent. In order to solve for x, we need to get rid of the 4, the exponent 4. And if that was a squared, everybody would know what to do. You square root, opposite operation. Well, that's the same thing as having an exponent 4. In order to get rid of it, we take the 4th root. Now, the 4th root of 81 is 3, so this works out well. 4th root of 81. 4th root of x to the 4 is just x. And the 4th root of 81 is equal to 3. Now, one thing I want you to think about here is when you want to isolate a variable that has an exponent, when we isolate it, what we're doing is getting the exponent to become 1, because x equals 3 is x to the 1 equals 3. That's what we want. So one way to look at this is to raise x to the 4th to an exponent that when you multiply these exponents, it equals 1. And that is always the reciprocal. When you multiply any number by its reciprocal, it equals 1. So this product equals 1. And if we do the same, raise 81 to the same exponent, then we get our answer. And hopefully you all realize that raising it to the power of 1/4 is just exactly the same as the 4th root. But thinking about it in this way, it helps us to solve questions like number 2. How do I get rid of a fractional exponent? Well, I raise it to its reciprocal. So instead of thinking of this as a cube root squared, kind of confusing when I want to get x by itself, I'm going to raise x to the 2/3 to its reciprocal. And do the same to the other side, because that's what equations, you have to do the same thing to both sides. Now look what happens when I multiply x to the 2/3, well, the exponents, multiplying the exponents, 2/3 times 3 over 2 is x to the 6 over 6, which is x to the 1. When I take 4 and raise it to the power of 3 over 2, denominator is the root, and exponent. Numerator is the exponent. And 4 is a perfect square, so that's 2 to the power of 3, which equals 8. So x is equal to 8. So when you see fractional exponents, you can always get rid of them by raising both sides to the reciprocal. All right, how about this one? We have a binomial in the bracket. So that's 3 over 2. We want to get rid of that. In order to isolate x, we have to isolate the bracket, get rid of the exponent first. So we're going to do the same thing we did last time. Raise the whole thing to the 2 over 3. 2 over 3. And 3x minus 5 is raised to the power of 1 because the product of reciprocals is 1, and I don't have to write exponent 1 anymore. I don't even need a bracket. 3x minus 5 to the power of 1 is just 3x minus 5. Now, 27 to the 2/3, cube root of 27 squared. Cube root of 27 squared. 3, cube root of 27 is 3. Squared is 9. So this side works out nice and simply to 9. 3x minus 5. So we can continue and solve this nice simple equation. We're going to add 4. My mistake, we're going to add 5. Add 5 and get 14. Divide by 3 and get 14 over 3. So x is 14 over 3. Next one. Now here we're going to solve, those were not exponential equations. Now we want to solve exponential equations. What we're going to do with exponential equations is to try to write both sides of the equation with the same base. Now if that's not possible, then we can't use the algebraic method to solve it. We're going to be able to do that later in the chapter, but right now, if we can't make them the same base, we can't solve it algebraically. We can solve them on our calculator, y1, y2 intercept, but not algebraically. Most of these examples, we are going to be able to write them as the same base. And once you have them as the same base and one base and exponent on both sides, then you can drop the base. Equate the exponents. This is where you drop the base. And once you drop the base, you make the exponents equal to each other. And then we can solve for the variable. You'll know exactly what I mean as soon as we do this first example. All right, nice, easy one to start. We don't even have to change the bases. They are already the same. If you have one power on both sides, in other words, one base, one exponent, here's your exponent. I'm hoping everybody can see here that if these are both base 5 and they're equal to each other, that means that this exponent has to be equal to this exponent. So we no longer need the base. We just go right to this step. That's what I mean by drop the base. All right, now we have 2x plus 3 equals 7. We can solve for x. And nice thing about equations, always easy to verify. So if we have a 2 for x, that's 2 times 2 plus 3 equals 5 to the 7. And 4 plus 3 is 7. And it's an easy check. So with equations, should be checking every time. Let's do this one. Obviously, a little more challenge here. We don't have a common base, but hopefully you recognize 9, 81, and 27. You won't get examples that have really large bases. So you'll be seeing examples base 2, base 3, base 4, base 5, possibly a little higher, but most of them are just those bases. So if you recognize powers of 2, powers of 3, powers of 4, it's going to make these a lot easier. And this is obviously powers of 3. We could leave it as base 9 if it was just the 9 to the 2x plus 1 and 81 to the 4. But 27, it's not an easy change to make it a base 9. So let's use base 3. So what I've done here is just change the 9 into what I know it equals, 3 squared. Change 81 into what I know it equals, which is 3 to the 4. And 27 is 3 to the 3. I've substituted the 27 with this, the 81 with this. The exponents that were already there are still there. Now I have to use my laws of exponents back on the review page. When you have an exponent raised to another, you multiply. So let's get the products here. So we're getting there. Now that we have the same base, what we have to do before you can drop the base, you can't drop the base at this stage. You have to simplify until both sides are 1 power. So this side is okay. Now the rule with this side is that your bases are the same and you're multiplying. So this is going to be, when you're multiplying with the same base, add your exponents. Okay, now we are at the point where we can drop the base. Okay. Isolate for x. So I'm going to minus 3x, subtract the 2, and x equals 14. Now I should be verifying, does that work? Let's go back up here, very beginning, and put in 14. So if we have 9 and 2x plus 1 is 2 times 14 plus 1, 28 plus 1 is 29. Wow, that's a huge number. So I'm going to let you work that out and verify on your own. Make sure it works. It is a very large number. Okay, let's do the next one. Now you have a choice for this one. We could use the base 1/5, or we could use the base of 5 and make your exponents negative. I think I'll just leave it as a fraction and leave the base as 1/5. I'm going to rewrite that. We don't need so many brackets. If I leave the base as 1/5, I think I better leave the bracket because then it's only going to look like the numerator is squared. Okay, I'm going to leave it like that. Equals, because 125 is 5 cubed, 1 over 125 is 1 over 5 cubed, and we already had an x plus 1. So again, we multiply our exponents. So this is going to be 1/5, 2x minus 4. Now we have one base on both sides and one exponent on both sides. They're binomial exponents, but now we can drop the base. All right, now we end up with 2x minus 4. I'm going to subtract the 2x from this side to leave just an x, subtract 1 from this side, and I get x is negative 5. Again, verify, verify, verify. So negative 5 minus 2 is negative 7 on this side. Negative 5 plus 1 is negative 4. So check to see that will equal. Those will equal each other, and then you know for sure that you have it right. Next. All right, this doesn't look as good. We have a 9, a 2, and a 73. I don't recognize those as being able to write them with the same base, but I do notice that the 73 and the 2 cubed have no variable. That means that I can combine them. Look at what happens now. I can add 81. I'm sorry, add 8 to both sides. And I'm already thinking of that 81. 73 plus 8 is 81. Now you have a choice again. I can write these both as base 3, but I don't have to if I recognize this one is already base 9 and this one is an easy change to base 9. Now I have to drop the base. So make sure you check for that. If you don't have numbers that work nicely, you can move one, especially when there's no variable here, move it to the other side to combine, and then it should look much better. 32. I recognize 32 as a power of 2. So just to make sure 2 exponent 6, no, it's 2 exponent 5 is 32. So if we have this exponent raised to another product, I have to multiply. This time it looks a little different because I get x squared minus 4x equals 2 to the 5. Now we can still drop the base here. We have 1 power on both sides, base 2. So that means we end up having to solve a quadratic, which absolutely no problem for you guys. So when we do that, we get 2 solutions. Do they both work? So here's a time where checking will be good. 5 and negative 1. So let's go back up here. X is equal to 5. 2 to the 5 minus 4. Sorry, that's 4. Raised to the power of 5 is supposed to equal 32. 5 minus 4 is 1. 1 times 5 is 5. So that definitely works. Our other choice was a negative 1. Let's see if negative 1 works. If we have 2 to the negative 1 minus 4 raised to the negative 1, is that going to equal 32? Well, this is 2 to the negative 5. Negative 5 times negative 1 is positive 5. So yes, that works. I cut off my check there so I wouldn't run into the next part, but both of those are solutions, and we wouldn't know that unless we check. Okay, let's try this. 256, 64, dividing. I recognize 64 as a power of 2, and 256, let's check. 2 exponent 6 to 64. 2 exponent 8 is 256. So remember, we can write the roots as our denominators, and that is going to look like, so we said 256 was 2 to the 8. 64 is 2 to the 6. So recognizing them as base 2 would be the first step. And now changing the roots, we don't have laws of radicals like this. We need to change them into exponents so that we can work with them. Now this is going to be a denominator of 5 and a numerator of 8. Denominator of 6, numerator of 6. Well, that's 6 over 6. All right, we can't drop the base at this point. We need to, again, use our laws of exponents. Dividing with a common base means subtract your exponents. So we can write this as a single exponent, and what we're going to do is 8 over 5 minus 1. And when I subtract 1, that's the same as subtracting 5 over 5. 8 minus 5 is 3. So this is equal to 3 over 5. And I'm writing an x here. I'm already solving it. I can see by looking at it now. We don't have to even drop the base to know that 3 over 5 equals x. End of problem. But again, to be certain of your solution, go back and check to make sure it works. All right, let's see about this one, just to see how much we have left here. Just two more. Number 7 looks very different. So what I want you to recognize here is this middle bracket. That middle bracket is going to give this type of problem away, because I'm going to let 2 to the x be a different variable. If we let 2 to the x be a, then the middle term is going to become minus 10a. But look at this. If we say 2 to the x equals a, then what is 2 to the 2x equal? Well, 2 to the 2x is going to be the same as a squared, because 2 to the x squared is 2 to the 2x, because we would multiply those. So this is the same as a squared. So I'm going to write that as a squared minus and look at that quadratic. Once you substitute, this problem becomes so much easier. So we're going to write it as factors, and we have a minus 8, a minus 2, a equals 8, a equals 2. So that's great. We know what a is, but now we have to go back. Remember these trig questions that were kind of like this? We substituted a variable in, and then we have to go back and solve for x, because we said 2 to the x is a. They work out pretty nicely, don't they? 2 to the power of what is equal to 8? Or we can change a base and write 8 as 2 cubed to realize x is 3. And look at x, 2 to the x is 2. That means x is 1. And those are the two answers to this problem. And once again, substitute them back in and make sure that they work. Okay, I'm going pretty quickly here, but I want you guys to pause and stop and do these problems yourself before you see me work through them. You definitely don't have to go at the same rate that I'm going. Okay, again, a different looking problem that you'll see in homework. So what do we have here? Those first two terms with the same base actually have a common factor. Very hard to recognize the first time you see this. If you see this, 2x plus 1, it actually has a factor of 2 to the x. If I take out 2 to the x, it's like dividing this by 2 to the x. What would that equal? Well, when we have a common base and we're dividing, we would subtract. The base stays the same. X plus 1 minus x is 2 to the 1. X minus x cancels, and you're left with just 2 to the 1, which is 2. So this means that I can take out a factor of 2 to the x. So when I divide 2 to the x plus 1, right here, when I divide that by 2 to the x, I get 2 to the 1. When I divide 2 to the x by itself, that's 1. So what I have here is 2 to the x times 3. 48 divided by 3. And 2 to the power of what is 16. You might be able to see it by now. If not, we can change them to the same base. 2 to the 2 is 4, 2 to the 3 is 8, 2 to the 4 is 16. X is equal to 4. So tricky for the first time you see that, but with the base is the same, you can divide out a common factor of 2 to the x. All right, end of lesson 2. We'll work on this assignment in class tomorrow.